We're going to do a couple problems on the concept of circular diffraction. So this has to do with a beam of light that's coming and going through an opening that's circular in nature. Okay, so the beam of light comes, and it's circular in nature. The diameter of the opening is A, and the beam of light, so it could be something like this, circular opening, and the beam of light diffracts outward, okay? And then on a screen, it forms a circular diffraction pattern, okay? So there's gonna be a central maximum like this, central maximum, and then there's gonna be a destructive interference, and then there's gonna be a first order maximum like this. The first order maximum is going to be much thinner, usually. The central is going to be much thicker. So there's going to be central maximum, first order minimum, first order maximum, and then second order minimum, and so on. So it's similar in concept to the regular single slit diffraction, okay? But this time it's applied for circular object. This is applied to such things as, for example, when we try to look at a light source and our cornea is kind of circular in nature, and every time we try to see an object, the light of that object comes into our eye and diffracts. Now the one that we see, the pattern we see, is primarily the center one, but there is a little bit of a diffraction, so there's actually the first order maximum, second order maximum, and so on and so forth, right? So if there are two objects that are kind of close to each other that are far away, and if they're kind of too close to each other, right? Let's say there happens to be a car with two light beams like this, okay? And the two light sources come through and diffract, and they both form a diffraction pattern, right? If the car is too far away, what might happen is the diffraction pattern of one of the light sources might interfere with the diffraction pattern of the other and overlap. It might be something like this, let's say. There might be some overlap happening, okay? And so if the two light sources coming from the car are too close to each other and too far away, we might not be able to distinguish them as being two light sources. What is the equation governing this? Well, it's very similar to the equation governing single slit diffraction. For single slit, the equation is A sine of theta is equal to m lambda, where m is equal to 1, 2, 3, 4, 5, and then this gives you the angle to the first minimum, second minimum, third minimum, and so on like that, right? To either side of the diffraction pattern. So I've talked about that in my previous videos on diffraction pattern. For circular diffraction pattern, the equation turns out to be A sine of theta is equal to 1.22 m lambda. So there's an extra factor of 1.22 that comes about when we derive the equation of the circular diffraction, right? So what's going to happen, we're going to ask a problem such as this. We have a question now of this type. It says, a light beam of wavelength 580 nanometers is incident on a circular hole slit of diameter A is equal to 0.12 millimeters. It says, find the size of the central bright circular fringe on the screen 5 meters away. Okay, so this would be a good example of a type of question that you would apply this equation to. Okay, so the wavelength is given to you, 580 nanometers. The diameter is given, 0.12 millimeter. And we want to know what is the size of the brightest central ring, right? So basically the picture will look like this. So if this is the opening here, and you draw a picture like this, well, we're going to assume that the opening is so negligible compared to the distance to the screen. The screen was 5 meters away, right? 5 meters away, this way. And then basically we have here, it goes like this, and then this is the circular pattern, right? This is the central bright fringe here, the circular central maximum. So this distance here is the, we're gonna call y, right? We can call that the radius from the center to the first minimum. And then here we have the first minimum, it's dark. And then after that, the second fringe begins. It looks like a ring, right? So we just want to know the distance from here to here, y sub 1, okay? This distance is the distance to the screen D. So now we use this equation, a sine of theta is equal to 1.22 m lambda. Now sine of theta, this is theta here. We would usually have to go, sine of theta is y over the hypotenuse, and the hypotenuse is y1 squared plus d squared. But we don't have to do that. We can assume the angle is so small, the opening is so small, that the distance to the screen dominates, okay? Therefore, the angle theta is small. So for small angle, for small theta, therefore sine of theta is approximately equal to theta, which also approximately equal to tangent theta, okay? So when an angle is small, the sine of the angle approximately equals the angle measured in radians, and that's also approximately equal to the tangent of the angle. So it's much easier for me to take the tangent of the angle now, y1 divided by d, instead of doing this square root of y squared plus d squared. So therefore I can replace this a y over d, y1 over d, that's equal to 1.22, and my m is 1, because I just want to know the distance to the first bright fringe. So the size of the bright fringe there. So I just put here 1. Okay, the lambda is 580 nanometer. 580 nanometer. Okay, so let's calculate this. 580 nanometer. So then when we calculate y, we have y equals 1.22, 580 nanometer, and then we multiply this by 5 meter. Okay, then we can bring this down here, 0.12 millimeters. Now I can convert everything to meter. I can say 1,000 millimeter is 1 meter, right? And then I can say 10 to the 9th nanometer is 1 meter, right? So the meter will cancel the meter, the millimeter will cancel the millimeter, the nanometer will cancel the nanometer, and then my final answer will be in meters. Okay, so let's see what this comes out. 0.02948 meters. Now I can express this either as centimeter or millimeter. I can multiply by 100 and say 2.948 centimeter or 29.48 millimeters. So roughly speaking, what are we looking at here? We have a wavelength of light, 580 nanometers. The opening was 0.12 millimeter. 0.12 millimeter you could barely see. It's very, very close. But then we have a screen 5 meters away. That's quite far, 5 meters away. The size of the first bright circular ring will be what? 2.948 centimeters. That's quite big actually. 2.948 centimeter will be something looking like 3 centimeters like this, 3 centimeters down like this, 3 centimeters looking like this, like this, like this. So this 2.948 centimeters, 2.94, 2.94, 2.94, 2.94, so something quite big. Surrounding that, you're going to have rings like this, and the intensity of them is going to drop pretty rapidly. But you mainly see the center one and maybe the first one, okay? So now you can see how to do this kind of problem. Next, I will do a related problem to this, okay? Thank you.